sharing my screen. So give me 1 second. Yeah, probably you will be able to see the screen now. Is it visible to everybody?
Yes, yes, it is visible.
Okay. First of all, I would like to thank the organizer for giving me the opportunity to give the talk. Uh, there are so people are saying in the chat that it's not visible. Now is it visible? Uh, is everything clear? I'm audible. The screen is visible. Any problem?
Yes,
Now
it
it's
is visible and you are audible.
okay. Okay. Thanks. Thanks. Okay. So let me again thanks the organizer. So particularly for me, it's a very special thing because I was born and brought up in Asansol. So my home is 5 kilometers away from BC College, and I grew up there, B, BB College and BC College. And these are the institute I have seen in front of my eyes. So it's actually an honor for me to uh, deliver my talk in a conference organized by Bidhan Chandra College. So I'm going to talk about conjugation invariant norms on diffeomorphisms. And this will be an introductory talk. So I will introduce the basic objects, what are the problems, and what kind of solutions we are looking for, what kind of solutions we are trying to solve. And this, I will keep things as basic as they can. And at the end, I will probably say something about the current research work of me and probably the other people. So at any point of time, if you have any doubt or any question, please feel free to ask me at any point of time. Okay. So what is the main object? So let us start with a simple thing that we all know. So suppose we start with V. This is a vector space over either real number or complex number. So we start with a vector space over real number and complex number. So for a moment, I won't restrict myself to finite dimension, but for this discussion, dimension doesn't matter. So if you want, you can keep yourself, you can think of this V as Rn or Cn. Okay. And so in any such vector space, there is a particular operation you can put, there is a particular extra structure that you can put, and that is called norm. Okay. So you can put a norm on a real or complex vector space. Okay. So what is norm? Let us recall what is norm. So norm is a function from the vector space to positive real numbers, and it has the three properties. The first property is, let me rotate the screen, that will be easier for me to write. Yeah. So the first property is norm of a vector is 0 if and only if the vector is the 0 vector itself. That's the first property. Sorry. If and only if V is 0 vector. So this is your first property. So norm of a 0 vector is only 0 norm element you have in the vector space. What is the second property? The second property is you can mod out things. So if you take scaling of a vector by a scalar alpha, then the norm will be mod of alpha into norm of V. And you can think of this nu as our standard notation. I'm just using this for particular reason. Okay. And this is for all R alpha belongs to the scalar field, whichever field you are working on. And the third one is sort of our usual one, which is, so with these two properties, we get this, we have this extra property with this norm, which is the triangle inequality, which is this one. Okay. So these are the three properties that we require for a non-linear space, vector space over R of C, and we want to put a norm, and norm should has these three properties. And as we know that once we have this thing, you can define a distance by just getting the norm of the difference between two elements. Okay. So now the question is, this is a vector space, right? So we have a vector space, we have given a norm, and it should satisfy these three properties. So a question is, So a general question, can we introduce a norm on a group? This is kind of the question. Okay. Can we introduce a norm on a group? We can understand the norm on a vector space, but now we want to introduce the norm on a group. So let us see what are the properties that are very clear. So suppose, so I want to mimic these three properties, property 1, 2 and 3 in case of a group. Okay. So let us start with the group. So let G be a group. And I don't have any restriction over the group. You can take your favorite group, anything, finite, infinite, Lie group, uncountable group, whatever you want. Start with your favorite group. Okay. And so we want to introduce a norm on the group. Okay. So again, I will mimic this property first. So I will go one by one. So I will mimic first this property, that a norm should be a map from G to the positive real. Secondly, I will mimic this property, property 1. This I have to worry about a little bit, and this we will see that we can mimic quote unquote straightforward. So let us see. So suppose I will call this a length function. So a length function on G. So here I have denoted it by nu. In this case, I will denote it by L. L is a function from G to again positive real numbers. And what are the first properties? So as we have seen earlier, L of E is 0. Let's say, let me write it. L of G is 0 if and only if G is your identity element. So that's my first condition. That is the same condition here. That's the same condition here. Norm of a vector is 0 if and only if the vector is itself 0. So that's the same condition I am putting. Except now vector space I have 0, on a group I have the identity element. Okay. Now let us go to the third condition, because the third one I can, if you look at the third condition, it says if you take the sum of two vectors and then you take the norm, then its norm will be less than equal to the norm of the individual element. Now this sum comes for the vector space. In vector space you can add two elements. Well, in group you don't have addition, but you have a group operation. So you can exactly keep this thing as it is. So rather than just taking the addition, you take the group operation. Okay, so let me denote the group operation by star. So let's suppose G star is your group. Okay, just for the notation. So then this will be L of G1 plus L of G2. Now, here is the interesting part. If you focus on this condition of the scaling condition of norm, now vector space has a scalar multiplication. You can multiply alpha vector by a scalar. But there is no such scalar multiplication in a group. In a group, you don't have a scalar multiplication. Okay? But if you think for a moment, you realize that if you are just working on R, if I replace this R by Z, if I suppose put alpha equal to 2, then the left hand side will be norm of 2V and the right hand side will be 2 into norm of V. So in place of alpha, I can put an integer. Okay, I can't put a real number because in a group you don't have a scalar multiplication, but you can put an integer in place of alpha. Okay, so let me try to do this in 2 steps. In the first step, I call it 2a, and I will start with this one, that every element and its inverse should have the same length. So remember, G inverse is, you can think of in vector space, you have V and minus V. So in group, you have G and G inverse. So you just replace G with G inverse and you want the norm of V and norm of minus V to be same. So similarly, in a group, you want the length of G and length of G inverse to be same. That's the first restriction. And the second restriction, as I said, that you can't take n alpha, right? You can't take n into G in a group. There is no such scalar multiplication. But you can always talk about G to the power n. That's just abelian versus non-abelian. In abelian notation, you write G plus G n times, that is Ng. In non-abelian, you take G dot G, that is G to the power n. So n into G is same as G to the power n when you are talking about multiplicative structure of the group. Okay. So rather than taking any scalar, I can take integer and I can ask for this. So these are our four conditions. I have a group and I would call a function a length function if length of a zero element is 0 and it's the only element with length 0. Length of G and length of G inverse are the same. Length of any power of G is the length of G multiplied by mod of that power. So length of G square will be 2 into length of G. That's just the scaling from the norm. And then you have the triangle inequality as it is. Length of G1 into G2 in group is less than equal to length G1 plus length G2. Okay. Now you may ask, like, why do we care? Why such a there's a question, length of G to the power n equal to mod G into, so remember this, I haven't put star because you see mod n into G, mod n into LG, on the right hand side you have real numbers. Okay. So on the right hand side, mod n is just a, so this n is integer. So on the right hand side, you have real number. You know what multiplication is. The dot is just multiplication. Okay. Yeah. Okay. So these are the four conditions I have. Now you may ask, why do I care? Why do I bother about this kind of things? Okay. So let us start with a very simple example. So this is example. When do we have such example? Okay. So the easiest example is consider R with mod. That's a norm vector space. Okay. So that automatically satisfies this. This is generalizing. I'm generalizing the norm. So everything which is norm in a vector space should automatically satisfy this. But then how do you get groups? You see, Z has this, R has these subgroups. Z is a subgroup of R. There are many other subgroups. Rational is a subgroup of R. Okay. I'm saying subgroup with addition. Okay. So when you restrict the norm, if you restrict the modulus of R in rationals or in integers, you will get automatically an example of such thing. That's just like straight away. That's how you define it. You define it as a generalization of a norm. So once you restrict to a subgroup of a vector space, it automatically satisfies all these properties. Okay. That's the first thing. Well, this is the easiest example. Now you can simply generalize it. You can take nth power of R with the L2 norm or L1 norm or LP norm. I will put a small p here, doesn't matter. And then you can take Zn or Qn, all of them will give you groups with this kind of norm. Yeah, so what do I mean by restriction of a map defined on a group? It's a map, a function from A to B. If B is a subset of A, then you can restrict the function F to B. So that is always well defined, right? You can restrict a function. So this function, remember, these norms are functions. They're functions from vector space to 0 infinity. So you can restrict those functions to a subset. So Z is a subset of R, so you can restrict. Okay. So that's what I mean by the restriction. Yeah. Okay. Now, okay. So now, okay, we have defined something. We have had some examples, but they're not much interesting example, because if you look at this example, all of them are abelian, and they're coming from kind of like you are restricting a norm to a subset. You are not doing much. Okay. It's basically the same thing. So if you can ask the first question, and the question is, does there exist a non-abelian group which admits a length function? So that's your first question. Yeah, so you can ask this question that does there exist a non-abelian group? I have given you all the examples which are abelian. Can you give an example which is a non-abelian group and where you have a function L which has all those three properties? Okay. Yeah, so Madhu Krishna, that's exactly what I'm saying. Yeah. Yeah, so you can ask this question. So can we have a group, a non-abelian group where we have a length function? You can ask this question anyway. Does there exist a finite or an infinite or anything like that? So this question was due to Apurva Khare, and he asked this question to Terence Tao. Okay. So Khare asked this question to Terence Tao in a discussion, and so then they started a project in online. I mean, they didn't start it. I mean, the project was already there. It's called Polymath project. So Terence Tao earlier, I forgot his name. Yeah. So they started this project, Polymath project, a particular problem to attack this problem, to solve this problem. Can we construct a non-abelian, can we have a non-abelian group and construct a length function? Okay. And collaboratively, they solved the problem in 2018. So let me state the theorem for you. So this is the theorem, and this was proved by DHJ Polymath in 2018. Okay, so let me tell you something about this DHJ Polymath thing. This is not the name of a person. Okay, so DHJ Polymath Polymath program was started by Gowers, and he tried to solve certain problems in number theory, and he started this online collaborative systems where somebody in his blog post will post a problem, and at the bottom you will keep on suggesting your suggestion, and ultimately people will combine them, and you will get to a point where you will be able to solve this problem. And the first Polymath project was very, very successful. This is density Hewitt Jewell problem, and that they solved the problem in such a brilliant manner, and that they continued this Polymath program for many such problems. And one of such problem is this one. And one of the main contributors of these problems who solved this problem was Tobias Fritz, Siddharth Gadgil, my advisor, Pierre Nielsen, Silberman, and Terence Tao, of course, Terry Tao and Apurva Khare. So these are some people. There are many people who contributed to this problem. So what was the statement of the theorem? The statement of the theorem is that if G admits a length function, then there exists a Banach space B with the norm such that G embeds into the Banach space and the length function is the restriction of the norm. Okay. So what they proved was, yeah, I'm coming to what is Banach space, but that's not important. But just if you don't know what Banach space is, just think of this as non-linear space. This is not important. You're just a vector space with a norm. Okay. Yeah. So what they proved was quite bizarre. They proved that the only groups which can have the length function are the abelian groups. So in particular, these are the only examples for which you can construct a length function. There has to be inside, if you're considering some finite dimensionality or something like that, it is always some Rn or Cn where your group is sitting. If it is infinite dimensional, some Banach space where the group is sitting. Okay. So that's all. So if you try to mimic the conditions on the norm on a group, the only type of group you are capable of achieving are the groups you are getting by restricting a norm on a vector space. That's all. So basically understanding a group with the length function is same as understanding a vector space with a norm. You don't have anything extra. So somehow this was kind of surprising. So only group which admits length function are the abelian. That's not an interesting story. Well, actually, this property was quite controversial. This particular property, and all these theorems, actually the theorem which they proved, this actually exploit this property quite heavily. So now the second question is, what happens if you remove this property and if you introduce some alternative property which is a little easier to handle, which is a little lucid, for which you can get interesting examples of length function in a group. Okay. So can we get rid of a property this, and can we replace it with some property which gives us nice groups with nice length functions? Okay. And that is going to be my second and main topic of this talk. And I will call, this is called conjugation invariant. Let me use a different color for this. Conjugation invariant norm. Okay. So what is a conjugation invariant norm? So you have let G be a group. So a conjugation invariant norm, let's call it nu, from G to positive real, is a function such that you have these three properties. So the first one is this one. So all this property and this property remains as it is. 2a will also be there. Only I won't have 2b, and I will replace 2b by the following one. So 1 as above, same as above, 2a same, 3 same. Only thing that you change is 2b, and this is the property that makes things interesting. You want the norm to be conjugation invariant. This is the main property that we change. Rather than making thing absolute scaling invariant, you put the condition that if you conjugate an element, the norm remains unchanged. Okay. Now, if you look carefully about this property, this is automatically true in vector space because vector space is abelian. So in abelian group, this doesn't give you anything. Just G and G inverse will cancel out. So this property is particularly introduced for non-abelian groups. Okay. And one kind of fact that I won't go into, one of the part of the proof of this theorem due to these people, is that if you have a length function, then that automatically gives you conjugation invariant. So a length function automatically gives you a conjugation invariant norm. It's not straightforward. You can prove it that if you have a length function, that means if it is scaling invariant, then it automatically becomes conjugation invariant. There is a little lemma that you have to prove for that. So this conjugation invariant norms is actually a generalization of earlier ones. There's a question, a closure associative property is also followed while in defining a distance function over group. I don't understand what do you mean by that. I am just simply defining a function, not a homomorphism or anything. It's just a function. It's not even continuous or anything. Just a set function, which has these three properties. Okay. Now, okay. So now we are in a little bit of comfortable territory. Now we have these properties that we have a group and we have a function which has this property that, so I can write it. This is nu g is 0 if and only if g is identity. This was our first one. The second one is nu g is equal to nu of g inverse. This was second one. And the third one was nu g1, g2 is less than equal to nu g1 plus nu g2. So these are the three properties. Now again, I have the same question. What about examples? Do we have examples where you can construct a conjugation invariant group? Now, people who have seen a little bit of group theory or metric spaces, one of the things that you can do, you can construct to get a metric on a group is the following. So suppose your group G is generated by a set S. This set S can be finite, this set S can be infinite. So suppose your group is generated by this set S, okay? Then you can construct the word norm. What is the word norm of the elements? Word norm of an element? Well, you consider the minimum of such n such that you can write G as a product of n elements. N such that each Si belongs to S. So, remember you started with the group G which is generated by the set S. So, every element is a product of elements of the set S. Now, you take the minimal representative and define the minimum number of elements from S you need to construct G as the norm of G with respect to S. Okay. So, this is called word norm with respect to S. Word norm with respect to S. Okay. Now the problem is this gives you a norm, but this does not give you this property. This B property is not guaranteed for this norm. Okay. So other three properties you will get. It's not a hard thing. So what extra property do you need? So to have your norm to be conjugation invariant, what do you need? This set to be conjugation invariant. So now if S is conjugation invariant, what do I mean by conjugation invariant? If you take an element of a set S and you take the conjugate, yeah, S is the generator set of not a cyclic group. S is generator, S is any set. S is a set. It's not an element, it's a set. So any group can be generated by a certain set. You can take all the elements of the group. Okay. Anyway, so yeah, so if S is conjugation invariant, what do I mean by that? I mean that means that if you take small s from capital S, then if you take conjugate of small s by any other number, this again belongs to S for all G. Okay. Then this becomes a conjugation invariant. That's pretty much follows from definition. If you start with a set G, which is set S, which generates the group G, and you take the word norm with respect to that set S, then it gives you a norm, first of all, but that's not necessarily conjugation invariant. If you start with the set which is conjugation invariant to begin with, the norm automatically becomes a conjugation invariant. So this gives you a large class of examples, a large class of examples. So let me give you one such example. So concrete examples, what would be concrete examples? start with any group. Let G be any group. Okay. And let's say, yeah, although I will come to that question a little bit later. Okay. So let G be any group, and you start with particularly non-abelian group, because abelian we pretty much know what is happening there, and conjugation invariant doesn't make much difference. It's the same property. We're just adding G and G inverse, so they will cancel. So you start with a group, any group G, okay, and you consider the commutator group, the commutator subgroup. So this is called the commutator subgroup. Okay. So this is the subgroup generated by the elements of the form A, B, A inverse, B inverse, the commutator. Okay. Now the point is, if you look at this group G prime, this is generated by commutators, right? This is by definition generated by the commutators, and commutators are always conjugation invariant. Okay. So if you take the following, so call this S to be the set of commutators, okay, and if you take any G prime from the commutator subgroup, then the word norm, then the word norm is a conjugation invariant norm. Yeah, so I will explain. So what is, okay, so what is the commutator group? Commutator subgroup is a group which is generated by this type of element. A, B, A inverse, B inverse, where A and B belongs to the group. So you consider all the type of elements which looks like A, B, A inverse, B inverse, where A and B belongs to Z, and you consider the group generated by them. That is called commutator subgroup. Okay. So you can check the definition of commutator subgroup. It's available in any standard abstract algebra book. It's just a subgroup generated by it. Okay. And you can check, this is very easy to check. If you take an element of the form A, B, A inverse, B inverse, and if you take in conjugate of this G, A, B, A inverse, G inverse, then you can keep on putting G and G inverse in between, and you can write the whole thing as a product of conjugate of individual elements. Okay. So this gives you a conjugation invariant norm, and this norm has a special name. This norm is called the commutator norm, commutator length. Okay. So if S is your set of all commutators, so here I am taking S, the set of all commutators. Okay. So this is called commutator length. Now, why is this important? Like if you start with a non-abelian group and you take the commutator subgroup that always have a commutator length, which is conjugation invariant. So this is, now I will go to the particular reason why it is important. If G is a simple group, now I don't know the other, so G simple group means that G has no normal subgroups. Okay. So this is just no. This is A, B, A inverse, B inverse in any way you want. A, B belongs to group. So suppose your G is a simple group, then it doesn't have a normal subgroup. Okay. And it's a standard fact that this subgroup G prime is always a normal subgroup. Okay. So if your group is non-abelian, and if G is a non-abelian simple group, then G equal to G prime. Then G is the whole commutator subgroup. Okay. So we get that any non-abelian simple group admits a conjugation invariant norm. Invariant norm, namely the commutator norm. Any simple non-abelian group always admits a conjugation invariant norm. So now we have a huge class of conjugation invariant norm. So this is where the study, so this is the classical results, these were all known. And now people started asking questions about non-abelian simple groups. Now you have a huge class of group which admits a conjugation invariant norm, particularly the commutator norm. You can ask this simple question. And so this question was asked that if you start, so the question, if yes, non-abelian means they are not commutative. Okay, if G is a non-abelian simple group, then what can you say about this thing? So you take the commutator length, commutator norm, let me call this L of, call this nu of G, and G belongs to G. What can you say about this where nu is the commutator norm? So this is a general question. You start with a non-abelian simple group, you know that it has an conjugation invariant norm. Simple question, whether the norm is finite or not. If you take supremum of norm of all elements, whether it is finite or not. This is similar like asking whether a metric space is bounded or not. You have a length function, you have a norm, whether the norm is bounded or not. Okay? And if it is bounded, then what can you say about this? What can you say about the norm? So now we will focus on particularly two classes of examples. So this is first class is finite simple groups. And then we will see infinite simple groups. Okay. So now you have two classes of groups, a finite simple group and infinite simple group. So now you can ask this question, what happens if you start with a finite simple group G? What can you say about mu G supremum? G belongs to G. Okay, where nu is the commutator length. And this question is known as Ore's conjecture. So what is Ore's conjecture? Ore conjectured that if G is any finite non-abelian simple group, then supremum of nu G, G belongs to G, is 1. Forget about being bounded, it's 1. Every element is a commutative. So what are the finite simple groups we know? Now we know all the classification of finite simple groups, right? So one of the basic ones that we learn in our undergraduate is AN, alternative groups when n is greater than or equal to 5. And Ore actually proved this theorem for alternative groups, and later he conjectured that it should be true for finite non-abelian simple group. All finite simple groups should have this bounded norm under commutator length. And this was quite a remarkable conjecture, because how do you know? Like, there is a class of simple groups, how do you know? But this was actually proved to be true. So Ore proved it for AN, for all alternative group n greater than or equal to 5. They proved that this is true, and this was finally, so this was conjectured in 1950s. And this conjecture was proved So let me, the Ore's conjecture was proved in 2010 by the following people. This was proved by M. Liebeck, Oberyn, R-I-E-N, Anil Shalev, and P.F. Okay. So they proved the conjecture in 2010. So this was quite remarkable and it was not expected, but I mean, it was expected, but to get a proof which includes everything was quite surprising. So now let me come to this part, which is the talk of the topic in the heading of my talk. What about infinite simple groups? So what are the examples of infinite simple groups, by the way? So one class of examples of infinite simple groups are due to Thurston, and it was actually known before Thurston that if M is a manifold, is a smooth manifold, so just a finite dimensional, then if you take the diffeomorphism group of M and you take the identity component, then this is simple. And I need some more restrictions on M, but I'm just stating simple. So Thurston gave a class of simple groups in case of infinite dimension. These are actually uncountable groups. Okay? And so you can ask the same set of questions. So you can ask, okay, now I have a simple group which is infinite. For finite group, I know that the bound of the commutator length is 1. What happens if I go to infinite dimension? And most of this result, now I'm short of time, so I will just write down the result, the people who studied this, and conclude the conclude this session. So this was the first set of result was proved by Burago, Ivanov, and Poltrerovich, and they proved it for dimension of m greater than equal to 3. They pretty much proved everything. And then in dimension 2, this was a recent result by Hensel, Borden, and Webb. Borden, Hensel, and Webb. And this is when dimension of m is 2. And they proved it for diffeomorphism 0 group of M, where dimension M is exactly 2. So that's the only case left for Burago, Ivanov, Polterevich's thing. And I did some work related to this, but I consider not exactly diffeomorphism 0, but the whole diffeomorphism group. And we proved there is another conjugation invariant norm in that group, which is called the entropy norm, and we actually proved that the bound of the entropy norm is infinite. That means they are not bounded norms, they are unbounded norms. So you can have unbounded, you can have unbounded norm on infinite simple groups. And of course, there were earlier there were examples that were also known, but we proved it particularly for diffeomorphism groups of surfaces. That means dimension 2. So I think I would conclude my talk here. Do I have any more time, or is it okay?
You can take 5 more minutes.
Okay.
5 or 10.
Okay. So okay, I can take 5 minutes. Okay, thanks. Then I can say something about it. Okay. So when you talk about, okay, so let me say something about this object. So this is a class of simple groups. So what do I mean by that? This is group of all diffeomorphisms. All diffeomorphisms. So what are diffeomorphisms? So diffeomorphisms means you have a homeomorphism, that is a continuous map whose inverse is also continuous, and both the map and its inverse are smooth, that means differentiable. That's what it's called, diffeomorphism. Diffeomorphism means homeomorphism whose both sides are differentiable. Okay. And what is this 0 suffix means? This means the identity component or the homotopy classes of diffeomorphisms which are homotopy to identity. Okay, so you can think of this as sort of like you have some topology in the space and you consider the connected component which contains the identity. Okay, and typically when you have, so these two classes of groups, this Ore's conjecture that if you prove that supremum is 1 and for infinite case we have groups for which conjugation invariant terms are infinite, they use completely different techniques. So for finite groups, your techniques are completely comes from representation theory. You look at the characters and how characters behave of all the representations of the group, and that gives you the information. Okay. For infinite simple groups, it's different. So for infinite simple groups, what you do is you don't prove the theorems directly. Like you don't try to construct, try to check the properties of the norm, because now you have a huge collection of elements. So what you do is basically, how would you do it? So let me start with a simple object. Let's say, suppose you have let's say two metric spaces dx and dy, and you want to show that this metric space is unbounded. Okay. Now suppose you have a continuous map from this metric space to that metric space, and you know this is unbounded. Suppose you know this is unbounded, okay, and suppose this map is Lipschitz. For some constant, you have this property. Suppose this map is Lipschitz, okay. So now, what you can prove that if YD is unbounded, then you have sequence of elements whose distance goes to infinity. Well, this is called Lipschitz constant. So suppose your function is a Lipschitz continuous function, then you start with a sequence xn, fxn and fyn, and suppose this is, let's say, let's consider this to be surjective. Take a surjective map if you want. This is surjective. Then you start with two sequences in yn which diverges, which goes far away from each other. Then you can take k to be between 0 to 1 or anything. Like, yeah, you need k to be 0 to 1, yes. But for this, it doesn't matter actually. For this, it doesn't matter. You can take k to be between 0 to 1. For this, it doesn't matter. It will be just a constant. For this particular thing, you need constant. But for Lipschitz continuous, yeah, you need k to be 1. Anyway, so if this goes far and far away, what you can claim is this will go far and far away. So that is one way to prove unboundedness of metric spaces. Okay. So you can try to do the same thing while you have a group and a norm, and you try to do the same thing. You try to construct a function, and our usual suspect is R, which is unbounded, we always know, and you try to construct a continuous function. Okay. Now, the problem with this approach is that many of the time, finding first of all a continuous function from a group to R is not easy. Secondly, this group is simple, so you don't have a homomorphism from this group to any other group. So there is no such homomorphism type of function exists. Okay, forget about continuity, we can't get homomorphism. And so these kind of technicalities appear, and so rather than looking for homomorphism, you look for a type of particular maps which are called quasi-homomorphisms, sometimes called quasimorphisms. And so in homomorphism, you have this property that G1 into G2 is phi G1. I'm taking the right hand side to be real numbers. So this is your standard homomorphism definition from a group to R. For a quasimorphism, what do you do is you take the difference of these two and you claim that this is bounded for all G1 and G2. So this is called, phi is called a quasimorphism. Okay. So it is like a homomorphism, but you don't want equality, you want bounded difference between G1, G2, product of G1 and G2, and phi G1 and phi G2. So this is called quasi-homomorphism. And so when you try to claim the infiniteness of the metric, the distance to be infinite, you try to construct this kind of maps, they comes very handy. And this kind of quasimorphisms exist for a large class of simple groups and many other groups. Actually, simple groups, you don't have homomorphism because there is no kernel, there is no normal subgroup. So you look for something which is weaker than homomorphism. So this is kind of a natural substitute for homomorphism to study simple groups. And so quasimorphism has been studied quite a lot. So there is a dichotomy between quasimorphisms and, for example, the commutator length. So there is a theorem called buffer duality. So you can use those techniques to actually get information about the simple groups. So I will conclude my lecture here. Thank you very much.
We are very happy and feel proud to know that Dr. Arpan Kobiraj have a connection with Asansol. And thank you for your beautiful presentation.
Thank you.
And we all enjoyed it very much. Thank you once again.
Thank you. Yeah, so there is a question. Any suggestion about this topic? Yeah, so there is a book called, so let me just write it down. It's called Stable Commutator Length.
I think there is some basic questions that are not so important. You have already discussed it in your lecture. And if you have any suggestion, you can give it.
Yeah, so I'm just writing this book. This is by Danny Calgary. It's available in, I think it's available in online. It's called Stable Commutator Length. And so this book has kind of an extensive discussion about, sorry, Calgary. I think I have made the spelling is wrong. It's called, yeah.
Thank you very much for your, and we will enter into our last session.
Hi. Okay, so I will stop sharing this project. I think Daniel is already here.
Hi.
Hi.
I don't know if you can see me.
Yeah,
just a minute. Our last resource person is Dr. Daniel Alvarez Gavela. Dr. Daniel is now Simon postdoctoral associate and instructor of pure mathematics at MIT, USA. He has also instructor of mathematics at Princeton University and a member of Institute of Advanced Study. Dr. Daniel has completed his PhD from Stanford University, California. His research is in symplectic and contact topology. The title of his talk is The Flexibility of Causistic and Applications. I would like to request Dr. Daniel to deliver his speech.
Hi. Yeah, thank you very much for the introduction and for the invitation to speak. So I'm going to try and present from the iPad.
Okay.
Okay. So do you see that?
Yes, it is visible.
Okay, great.
It is visible.
Okay, yes, fine.
Great. So yeah, so thanks again. So let me get started. So I'm going to talk about the flexibility of caustics. Depending on how much time I have at the end, I will discuss some of the applications that we're currently investigating. But I wanted to at least make sure that I give an idea of what the topic of research is for the non-experts. So I will begin by talking just about singularities of smooth maps. What are they? What do we know about them? What do we not know about them? Then I will talk about the H principle, which is a technique that was developed by Smale, Hirsch, and Gromov, and many others to simplify these singularities when there is no algebraic obstruction to doing so. And then I will transition from the smooth world to the world of symplectic and contact topology, and I will talk about Lagrangian and Legendrian fronts, which are the analogous objects, the analogous singularities in that world. And then finally, I will talk about the flexibility of caustics, which is the H principle in that world of symplectic and contact topology. So if there's ever any question, just type it. I'm not sure what a feedback link is, but I'm just going to go ahead. Yeah, if I miss any questions, just feel free to interrupt me. So let's see. So what is a singularity? So consider a smooth map just from Rn to Rm. This is standard Euclidean space. Okay. So definition, a point X in the source is regular if the rank of the differential is full, i.e. the possible maximum, which is the minimum between the two quantities n and m. Okay, so for those are regular points, and the behavior of a function near of a smooth map near a regular point is uniquely determined. Rank dfx is the rank of the differential. The differential is a linear map. Oh, I think I lost. I think somehow someone else started presenting. Let me try again. Okay. So yes. So the rank. So the dfx is the differential. So near a regular point, the behavior of the smooth map is completely determined by the inverse function theorem, okay, or the implicit function theorem. So the germ of f near x, and let me not be precise and define the germ, I just mean the local behavior of the mapping up to change of coordinates. Is completely determined, and this is called inverse function theorem. Or sometimes when the dimension of the source and the target is not the same, you call it the implicit function theorem. Okay, so that's a regular point. Is that all clear? So okay, so then what is a singular point? Well, it's a point that's not regular. Okay, so it's just a point at which the rank of the differential is not as big as it could be. So that's a singular point. And then what is a singularity? Well, again, it's the germ of f at that point. But again, just think of local behavior near x up to change of coordinates. Okay, any questions about that? So that's just basic definition. So let's make sure we understand it. No, the singular point is a singular point of the mapping. So it's a smooth mapping between Euclidean spaces, and the point is it's a property of the point relative to a function. Okay, so let me maybe give some examples, and then it might become clear. So the first example that I can give, so if the rank of the differential is locally constant, then you actually have an implicit function theorem. So it all looks like in linear algebra. So I don't know, maybe it's Rn is Rk times Rn minus k, and then the mapping is just the identity times 0, so it kills. It has some kernel, and oh, let me. Let's do like this, and then maybe this embeds into Rk times R m minus k if n is smaller than m. So it just looks like linear algebra. Okay, so this is the very easy case. This is the very easy case in which you have a singular point, but the rank of the differential is locally constant. And in this case, it's just like before. There's this very nice theorem that completely determines the behavior of the function near that point. If the rank of the differential is not locally constant, then things are more interesting. So let's look at some low-dimensional examples so that we start to get some intuition. The first and most important example is the fold. Okay, so it's just a one-dimensional example. It's x goes to x squared. That's the germ. But we can see it, for example, as a map from R2 to R2, or indeed for any Euclidean space to itself by just stabilizing with some additional coordinates, which which are just hanging out. It's just the identity in the additional coordinates, and this is very easy to visualize, right? So you start with R2, and then you fold it in 3 space, for example, and then you project it down vertically, and what happens is there's a region in the plane where this map is 2 to 1 because it has 2 pre-images over every point, and at each of these red points, these are regular points. The differential is an isomorphism. However, along this line over here folds, the rank of the differential falls by 1. Okay, so sigma is a singularity locus, and you can even see what the kernel of the differential is. It's this distribution here. So this line field here is the kernel of the differential. Okay, so F is this composition here. Okay, so that's the fold. It's the simplest type of singularity. Any questions about that? Yeah, I mean that's what's happening. You're folding the plane over itself. Yeah. I don't know how. It's the formula is yeah, x squared comma y. Okay, so that's one singularity. Let's talk about a different one. Let's talk about the pleat. And the pleat is also a singularity that happens in 2 dimensions. The formula is now a little bit more complicated, but it's not too bad. So it's going to be x cubed plus xy and just y. Okay, and so let's try to understand what's going on here. So what's going on here is that there are 2 folds that are dying against each other, as in a standard wrinkle. So if you imagine that you just wash your clothes and you're about to go iron them, then what you're trying to get rid of is these wrinkles that appear everywhere. And I've just wrinkled now my plane, and I'm projecting it down on itself as before. But now what I'm seeing is slightly different behavior. I'm seeing that there's this region on top of these 3 sheets where the map is 3 to 1, and then it's just 1 to 1. So before it was 0 to 1 outside, and here it's 1 to 1. And you can see that the singular locus now has this cuspidal shape that I drew at the beginning of the presentation. It's a semi-cubical cusp. And if you look at the kernel of the differential, what's happening to the kernel? Well, it's transverse at all these points, and these are indeed fold points. But then at the center, it is tangent, and that's precisely when the pleat occurs. Okay, so here, this is a pleat. And all of these other points, they don't look the same, but after a change of coordinates near everyone, these are just folds, like we were seeing before. And so the pleat is the birth-death of 2 folds. Okay, any questions about that? Okay, so a theorem of Whitney is the following, that for generic smooth maps between surfaces, all singularities are either folds or pleats. So that's it. That's pleat is what I just defined. This it's any map from a 2-dimensional object to a 2-dimensional object that in local coordinates can be described by the above formula. Okay, so that's a theorem of Whitney. That's all you see. So maybe you're looking at a person, and they're looking at you or whatever, and you're looking at the surface. So you're here maybe looking at them, and if you could see, so this is my eye, and I'm looking at them. So if of course we're not opaque, but if you could actually see, we're opaque, but if we weren't, you would see that here this is a line of folds along the neck, and then there's a pleat, and this is also a line of folds, and there's another pleat here, and similarly, so it's all pleats, everything that we see, all of the outlines of our vision. Right. So, okay, so that's nice to know. So in 2 dimensions, everything is just a fold replete. So then one could ask, what about in higher dimensions? Generic smooth maps from an n-dimensional manifold to an n-dimensional manifold. And well, this was a question that was studied thoroughly by Arnold and his collaborators, and there was a whole school of mathematics devoted to understanding singularity theory in general. And the long and short of it is to abandon all hope. Okay, so there is no classification of generic singularities in arbitrary dimension. Moreover, nothing like that can be hoped for. It is absolutely, absolutely hopeless. There's infinitely many non-equivalent local models that show up generically. Moreover, I think starting in dimension 9, there's a continuous space of non-equivalent local models. At some point, the space of non-equivalent local models has infinite dimension. And then to make things worse, the generic models aren't even stable. So they appear generically, but after a small perturbation, they disappear. So there's really absolutely no hope of studying singularities of smooth maps generically. And so one must approach the problem from a different point of view, namely, one must choose very specific non-generic perturbations to get rid of complicated singularities. And that is the subject of the H principle. So that's my next topic. But any questions before we move on? What is generic singularity? It's just the singularities that you will mostly see. So yeah, I mean, generic is a little bit of a tricky word because it can mean different things in different contexts. Let me not be precise about it. I just mean there's no reasonable classification of singularities in higher dimensions, basically under any definition of reasonable that you might hope for. So the H principle. So what is the point? So basically, the point is that complicated singularities can nonetheless be removed if there is no algebraic obstruction to doing so. And here by algebraic, what I really mean is homotopy theoretic. So I mean algebraic in the sense of algebraic topology, as opposed to geometric. Okay. So let's see an example. Okay. The first thing, the first basic example, which in some sense is the birth of this theory, is the theory of immersions. Okay, so an immersion between two manifolds is a map that doesn't have any singularities. Okay, so it's a map from a manifold of dimension m. Yes. So I'm about to do so. So I'm about to do so in this particular example of immersion theory. Okay, so we're looking at immersions between manifolds, and I will denote by mn the space of immersions. sometimes we indicate that a map is an immersion by the following twiddly arrow. Okay, and then let me define a related space, which is the space of bundle monomorphisms from the tangent bundle of M to the tangent bundle of N. So this is the space of all capital F's, where capital F is a bundle map from the tangent bundle of M to the tangent bundle of N, and I demand that it is injective on fibers. Okay, but there is no connection whatsoever between the map little f and the map capital F, other than capital F is a lift of little f. But I am not requiring any anything else. They're just decoupled. So the space of bundle monomorphisms is a purely homotopical object. So always the maps are between smooth manifolds and the differentials are between their tangent spaces. Yeah, maps between smooth manifolds, differentials between tangent spaces. Okay, so so there's an obvious map from the space of immersions to the space of bundle monomorphisms, which is take a function that's an immersion and then set f equal to be the differential of f. Okay, so this is there's a clear map this way called the differential, but of course there's a lot more pairs capital F comma little f that don't arise in this way, because these pairs are very special. They have this property that capital F is the differential of the function little f. And what is the theorem? The big theorem of Hale of Smershen of Hirsch and Smale? Well, they proved that if the dimension of M is strictly smaller than the dimension of N, then this map is a, well, weak homotopy equivalence. Okay. So if you've never seen this before, then it'll take a moment to wrap your head around it. But the key point is that this is just sections of some bundle. This is purely homotopical. And so the Hirsch-Smale's theorem reduces the question of existence of immersions, which is a geometric problem, to a problem that is purely homotopical. As an example of the example, you can show, if you want as an exercise, that the fact that pi2 of SO3 is 0 implies the famous Smale sphere version. So I don't know if you've seen, there's a really nice video that has been circulating on YouTube for a while of an animation that someone made where Smale's aversion is shown, where the sphere gets turned inside out, and it's an immediate corollary of the theorem as I've stated it, together with the homotopical input that pi2 of SO3 is 0. So this is an example of how the H principle allows you to reduce geometric problems to homotopical problems. Okay, any questions so far?
Daniel, by weak homotopy means higher homotopy groups are isomorphic.
Yes, that's correct. Yeah, the only reason weak is there is because you don't want to get into what are the CW structures and that kind of thing. But yeah, just that means that is a good point. Thanks for clarifying. So isomorphism on all homotopy groups. Great. Okay. Okay, but what about when the dimensions of the source and target are the same? Well, Smale-Hirsch is false then. Otherwise, we could prove the Poincare conjecture very easily, but we cannot. So, in this case, we need folds. But we can get rid of all singularities more complicated than folds. If the analogous obstruction vanishes. And let me not tell you what the analogous obstruction is, but it's something similar. Is there a question? Okay, so this is pretty cool. So for instance, you can get a three-dimensional homotopy sphere or four-dimensional homotopy sphere, and then map it to the standard sphere. Use this to reduce it so that it's a folded map, so that it's basically an immersion away from a set of folds, and then all of the complication of the Poincare conjecture is contained in the locus of these folds, of how these folds are overlapping with each other. This doesn't mean it's helpful necessarily to prove the Poincare conjecture, but this is just a word of warning that even if your map only has folds, these folds can be quite complicated and can encode quite a lot of information. Okay. So, all right. So in the remainder of my talk, I want to now indicate how an analogous story exists in symplectic and contact topology. So for that, I want to introduce Lagrangian and Legendrian fronts. So I'll do that in in a specific setting, just because it'll illustrate the main point, and I don't think it'll necessarily be useful to talk in greater generality. So let M be a smooth manifold. Okay, and so recall, or if you haven't seen this before, let me tell you that the cotangent bundle has a canonical one form, lambda, which we sometimes denote PDQ because it can be written in local coordinates as PI DQI, where these are the momentum coordinates and these are the position coordinates. I.e. the QI are the coordinates along M, and the PI are the dual cotangent coordinates. Okay, and right. So that's the Liouville one form, and then let me define the cosphere bundle to be the cotangent bundle remove the zero section and then projectivize. Okay, so if you have a metric, a Riemannian metric, then you can identify this with just the unit cotangent bundle, which is just those covectors of norm 1. But you don't need a Riemannian metric to define it. It's an invariant object. It's an object that's defined independently of any metric. And then the distribution that is the kernel of lambda descends to a distribution, which I'll denote also by the same symbol on the cosphere bundle, and we call it the contact distribution. Okay. Okay, so now I can tell you what a Legendrin is. So a submanifold, same dimension as the base, is Legendrian if it is tangent to the distribution. Okay. Okay, so yeah, it's just the kernel of a 1 form, so that's the vectors that are killed by it. And that's what a Legendrian is. And then I need one more definition. So the map which goes from the cosphere bundle to M, this is called the front projection. Okay, so symplectic and contact topology arise by and large from classical mechanics. There's some it's the appropriate language in which to formulate the Hamiltonian formulation of classical mechanics, and contact topology in particular is very linked to optics. And so now we're going to see the same pictures that we had at the beginning. So yeah, so okay, let me just define the object of interest. So a singularity of the restriction of the front projection to the Legendrian, also called the wavefront of the Legendrian. So this is called acoustic. So let's see some example. Have m equals r2. Oh, sorry, I just realized I made a mistake here. I think for the dimensions to work out, the dimension of the base should be 1 more than the dimension of the Legendrian. That's better. Sorry about that. So okay, so then what's an example? So then you see contact topology is the natural home for this cusp picture that at this point we've seen many times. Because how does this lift? Well, recall that what is the cosphere bundle, right? What is the cosphere bundle? So you can think of this as hyperplanes in R2. And so the point is that although this cusp is a singular object, there's a smooth field of hyperplanes along it. And so this field of hyperplanes lifts to a smooth object, lambda. And now the front projection projects this down to R2, and it has this singularity precisely when the cusp turns around. Okay, so here, so this is a caustic. So, so that's one example. And then let me draw. So this we just usually call a cusp. And then let me draw for you another very famous one, which is called the swallowtail singularity. So here M is going to be R3. And I'm only going to be able to draw the front because I don't have enough dimensions. And it looks like this. So it's the birth-death of two cusps. So this point here is a swallowtail. And very much in the same way that a pleat was the birth-death of two folds, a swallowtail is a birth-death of two cusps. Okay. And these singularities, these caustics, are things that we're very used to. We see them when light reflects or refracts through a medium. It's a fun thing that you can do if you just take any cup and you take your phone and you put on the light and then you shine your phone down into the cup, then you will see this cuspidal singularity form. And then if you start moving your phone around and you're a little bit lucky, you will see two of these cusps being born and die together in a swallowtail, which will trace this picture that I drew as time goes on. Okay, so finally, let me tell you about the flexibility of caustics. And I'll try to formulate a precise theorem, but more important than the precise theorem is that you know that the same slogan works. Okay, so singularities, caustics are generically terrible. There is absolutely no hope of classifying the generic caustic or anything even remotely comparable. However, there is an obvious necessary condition to simplifying caustics, which is homotopical. And if that obvious necessary condition is satisfied, then you can indeed simplify them. So the obvious necessary condition is sufficient. So let me just write that down. So there holds an H principle for the simplification of caustics. If there is no homotopical obstruction to simplifying caustics, or let me be more precise. Let me be more precise to eliminating all higher caustics then this can be achieved geometrically, i.e. by homotopy lambda t of Legendrians. And here, what do I mean by higher? I just mean more complicated than cusps. Which, yeah, a cusp is one-dimensional, but of course you can multiply it by any other number of parameters to get a higher dimensional model. Okay, so the cusp is the simplest possible caustic you could hope for, and what the theorem says, which this is something that I proved in my PhD thesis, is that that is basically all you need. Let me just quickly indicate. Well, yeah, let me quickly indicate what the condition is. So what is this homotopical obstruction? Okay, so obstruction, well, we have M, this is S star M, and there is a distribution nu, which is tangent to the fibers of this projection. And so caustics are the same as tangencies of lambda with this distribution. So this is lambda, and at a point like this one, then there'll be some complicated caustic. And then what is the obstruction? The obstruction is to can you rotate the field of planes tangent to lambda so that it becomes transverse to nu, i.e., you have this field of planes. Actually, they're Lagrangian planes, if you know what that is, and it's important that the rotation only happens through Lagrangian planes, but that's only for the experts. And then the homotopical obstruction is, can you rotate this field of red planes so that it becomes transverse to the blue one, like I'm drawing here. And so you see, existence of such a rotation is a purely homotopical question. It's just a question of whether two plane fields are homotopic or not. And it turns out that is exactly what you need to apply the H principle. Okay, so I think I will end there. I will just end up by saying that this H principle and related results are having some applications, and currently in work in progress with Yasha Eliashberg and David Nadler, we're trying to use it for the arborealization program, which, roughly speaking, is an attempt to generalize the theory of ribbon graphs from open Riemann surfaces to Stein manifolds or affine complex varieties of any dimension. So I will end here. Thank you very much.
Yes, the question.
Sure. Yeah, I can post the.
Yeah, it's okay. It's a simple question. So I just want to know. So if you are particularly interested in this kind of things, where you are looking at the tangent bundle and you are looking the contact structure and the symplectic structure on the tangent bundle. But let's say I have a symplectic manifold or a tangent manifold which doesn't appear as a tangent bundle of some manifold. So do we have kind of a
Yes.
and you can study this has a natural generalization there?
Yes. I only stated this for cosphere bundles because I figured that was the geodesic to being able to state something understandable in the time allowed. But it works for any symplectic or contact manifold equipped with any distribution of Lagrangian plane. So the distribution doesn't even have to be integrable.
Oh, okay. Oh, so you don't need the integrability condition also?
Not even, yeah.
Oh, thanks.
Yeah. Yeah, and it's the same. You know, the obstruction is, can you rotate the tangent planes so that they become transverse to the ambient distribution. And then if you can, then there exists a Legendre isotopy or a Hamiltonian isotopy that at time one gives you something that only has full singularities with respect to that ambient distribution.
Yeah, so regarding that rotation, you mean, so you have some Riemannian structure you are assuming compatible with it, or some Kähler structure compatible with it?
Yeah, not really. It's so there's no this rotate is really just it's a much weaker thing than that. So okay, so let me just be a little bit more precise here. So let's say that a half an n-dimensional plane in this contact distribution is called Lagrangian if the differential of that Liouville form vanishes on it. And then let's write by capital Pi the Lagrangian Grassmannian. So this is just the Grassmannian of such planes over S star n. So its fiber is UN mod ON, the Lagrangian of Grassmannians in Cn. And so then the Gauss map is a map from lambda to this guy.
Right. Okay.
And so rotate.
Now I understand.
Rotate just means whether, it's homotopic as such maps. Like whether does there exist G prime homotopic to the Gauss map such that G prime, all the planes in G prime are transverse to nu. So it's just about whether two maps are smoothly homotopic. There's no Kähler structure or anything like that. It's really just a question of homotopy theory.
So it basically it's a two-stage homotopy obstructions. The earlier in low dimensional case you just have the obstructions of homotopy groups. Here you have the one obstruction for homotopy groups, and the another is the rotation homotopy obstruction. Is it okay?
Sorry, which one was the other one?
Yeah, so in the lower dimensional case you have just the weak homotopy there. So the obstruction is only on the homotopy groups. So you have those homotopy obstructions together with this particular one.
Sorry, in which other case? In what is the low dimensional case?
No, in the Snell's theorem, I mean.
Oh.
I mean, low dimensional, not.
Yeah, no, but I think it's kind of it's disjoint set of obstructions in the sense that here we're already starting with a smooth manifold. Like we're already starting with a smooth embedded submanifold.
Okay.
So no, I mean you're absolutely right that if you started with I mean, it depends what you start with, right? Like if you just start with a manifold that's not smoothly embedded, then yes, you need to first address the problems of how to embed it as a Legendrian, and then once you have that, you can think of this obstruction. And but there's a little bit of a subtlety because to embed something as a smooth Legendrian, it's harder than as a smooth immersion. You definitely need those obstructions coming from Smale-Hirsch to put it as a smooth submanifold, but then the condition of being Legendrian is actually a little bit subtle. There is an H principle for existence of Legendrian embeddings, but that is yet a different story. So I guess you would need those three pieces: the obstruction coming from Smale-Hirsch. Well, you actually need to make it embedded, so that's yet something else for the immersion. Then you need the obstruction to make it Legendrian, and then finally you need this one to simplify the caustics. But a word of warning that a lot of the Legendrians that are produced by the H principle for Legendrians are very special. There are these loose Legendrians that don't have any symplectic topology. They're flexible. A lot of Legendrians, which aren't produced by the H principle, but which one encounters in nature, aren't loose, and yet this theorem still applies to them. So sometimes you want to already apply this to something that you know is Legendrian.
Oh, thanks.
Okay, thank you very much, Dr. Daniel Gavela. I think you have answered all questions. Okay, thank you very much for your nice and very beautiful presentation. Now we have to conclude our whole program. First of all, I would like to thank our all respected speakers, Dr. Tapo Chatterjee, Dr. Unup Dixit, Dr. Arpan Kobiraj, and Dr. Daniel Alvarez Gavela for giving excellent presentation and making this webinar interesting and meaningful. I'd like to express my gratitude to our Honorable Principal Sir, Dr. Falguni Mukhopadhyay, for providing encouragement, support, and opportunity to organize this webinar. As no program can become successful with a single person, so I extend my heartfelt thanks to our mathematics department for their support. Thank you guys for making this webinar successful with your contribution. I am happy to express my heartiest thanks to our entire family of Bidhan Chandra College for making this webinar a great success. Our heartfelt thanks to all participants for active participation and making the webinar a very success. Thank you very much for your cooperation once again. Thanks a lot to one and all directly and indirectly involved in this program. Thank you very much.
Thank you, and we will take we take leave now. So hence I announce our session closed for this international webinar. Thank you.